This mini lecture introduces aqueous solutions and discusses how ionic compounds dissociate into individual ions in water, what makes something a strong electrolyte, and how to predict the solubility of ionic compounds. First, a little terminology for solutions. Some of these terms won't pop up until the next chapter when we deal with actual calculations involving solutions, but it made sense to start introducing them now. I like to use an everyday example for this, that of your morning cup of coffee or tea if you're a tea drinker, as it represents a homogeneous solution of several chemical compounds. When brewing coffee or tea, the substances that end up in the final cup represent the solutes in the solution. Most notably, this is the caffeine that is extracted from the coffee grounds or tea leaves, as well as any other compounds that give flavor to the final cup, or triglycerides that give that silky mouthfeel in a concentrated shot of espresso. These solutes become dissolved in the hot water when they are extracted from the organic material that makes up the coffee beans and tea leaves. In addition, you may also be someone who favors sugar or cream in your hot caffeinated beverages. And when you dissolve sucrose or fat and protein micelles contained in dairy products, you're adding solutes to the solution. The important thing to remember here is that the bulk of the solution is still made up of water molecules, but there are these other compounds that have been dissolved within the water. Therefore, the water itself has its own term, and we call it the solvent. In this class, we'll focus on solutions that use water as a solvent, referred to as aqueous solutions. But many different chemicals that exist as liquids can also be used as solvents to create solutions. So these terms are not unique to water-based aqueous solutions and can also apply to solutions that utilize other solvents. That's basically it for terminology. In order to have a solution, you need to have at least one solute and a solvent. And since a cup of coffee or tea fits that description, they are essentially caffeine solutions. When solutes dissolve, they will either form ionic solutions or molecular solutions. Ionic solutions involve an ionic compound that dissociates into separate ions when it dissolves in solution, whereas molecular compounds will dissolve so that there are individual molecules of the compound in solution, but you won't end up with any ions generated in solution. Notice that in both of the equations that are listed here for this dissolving step, that we use the aqueous label to indicate when the molecule is dissolved in water. So for the solid, we start with the solid, we end up with aqueous ions. But for the molecular liquid down here, once it's mixed with water, we give it that aqueous label to indicate that it's now part of a solution. Dissociation occurs due to an ion dipole attraction between the polar water molecules and the charged ions in an ionic compound. So this is something that's specific to ionic solutions. The partial positive charges on the hydrogen ends of the water molecule can be used to balance the negative charge of anions, and the partial negative charges on the oxygen ends of water molecules can be used to balance the positive charges of cations. These interactions represent attractive forces between the water molecules and the ions in the ionic compound, and they can be strong enough to rip the ions away from the bulk crystal solid, allowing them to exist separately in solution as solvated or hydrated ions, where water molecules surround the ion. Note that the water molecules are not bonded to the ions. Instead, the ion dipole electrostatic forces are what hold the cluster of particles together and don't represent true bonds. When writing dissociation as a chemical reaction, the relative ratios of the ions in the compound are preserved in the ratio of ions in the solution. So when dissolving potassium chloride, or KCl, as a solute in an aqueous solution, there is one potassium ion in solution for every chlorine ion in solution. When considering ionic compounds with polyatomic ions, the polyatomic ion stays intact and does not break down into further components. So when dissolving copper 2 sulfate as a solute in an aqueous solution, there is one copper 2 ion in solution for every sulfate ion in solution. Now, if the compound does not have a 1-to-1 ratio of cations to anions, then whatever ratio exists in the molecular formula is preserved in the solution. So for potassium dichromate, which has 2 potassium cations for every 1 dichromate ion, this same 2-to-1 ratio is preserved in the solution's ratio of ions when this compound is used as a solute. At the bottom are a sequence of images showing the creation of the solution, starting with potassium dichromate as an orange solid as the solute and water as the colorless solvent in the flask. Mixing these two together results in the orange solution on the right, which contains potassium and dichromate ions with a 2-to-1 ratio of potassium to dichromate. And you'll notice none of that original solid remains if this is fully dissolved. Since the ions created in solution have positive and negative charges, they can be used to conduct electricity, and therefore ionic compounds acting as solutes in aqueous solutions are also referred to as electrolytes. When an ionic compound fully dissolves in water, this means that every ion in the crystal solid produces an ion in the solution, and this is referred to as a strong electrolyte, as dissolving large quantities of the compound will yield high concentrations of ions in solution, which will be very effective at conducting electricity. However, some compounds may not dissociate very well in water, as is the case for some acid molecules. Remember that acids are considered covalent compounds or molecular compounds due to the lack of any metal atoms, but they also display ionic properties in that they can dissociate a hydrogen ion, leaving the remainder of the molecule with a negative charge. So they essentially form cations and anions in solution. However, for many acids, dissociation does not occur for all molecules of the acid that's dissolved, but only for a small percentage. So these types of compounds form weak electrolytes because large amounts of the compound dissolved in water yield a small amount of ions in solution, and they will not conduct electricity as well as strong electrolytes. If you look closely at this figure, you can see that there are only 2 of the 5 molecules indicated here that have hydrogen ions that are separated from the acetate ion. Only the molecules that have dissociated will be able to conduct electricity. So these remaining 3 molecules, or four molecules, sorry, there's 6 total molecules here. But these remaining 4 molecules, with their ions intact, will not add to the conductivity of the solution. Finally, compounds referred to as non-electrolytes do not dissociate into ions at all, and are therefore molecular compounds, such as ethanol. Ethanol can be dissolved in an aqueous solution where single molecules of the ethanol will move independently of each other, but since those molecules lack any charge, the solution cannot conduct electricity and is therefore considered a non-electrolyte. Hence, any compound that dissolves without dissociating into ions is considered a non-electrolyte. The next couple slides give some examples of these different classes of electrolytes. Acids that completely dissociate into ions in aqueous solution are referred to as strong acids and are therefore strong electrolytes. You'll notice that a lot of these are some of the common ones that I had on the nomenclature worksheet for you guys to memorize. The word strong is referring to the same thing in both of these terms, this idea that every molecule of the compound will dissociate into ions when placed in solution. Other strong electrolytes will occur for soluble ionic compounds, and we can determine whether an ionic compound is soluble by referring to the solubility rules for common ions. More on this a little later. Weak acids, as described a few slides back, are those acids that do not completely dissociate when placed into water. And some common ones are listed here, but pretty much any acid that is not one of the 6 strong acids listed in this chart will be considered a weak acid and therefore a weak electrolyte. Again, the word weak refers to the same thing in both these terms, this idea that only a small percentage of the molecules of the compound will dissociate into ions when placed in solution. Finally, non-electrolytes consist mostly of molecular compounds that never dissociate into ions in solution. But not all molecular compounds fall in this category, as we have seen with the strong and weak acids, which are technically molecular, yet they exhibit ionic behavior as previously described. Also, any insoluble ionic compounds would fall into this category as well, and they can also be determined from the solubility rules for common ions. Solubility of ionic compounds depends on the strength of the electrostatic forces between ions in the ionic compound and the strength of the attractive ion dipole forces between the ions and the water molecules that we described previously. If the ions are attracted to each other in the crystal more than to the water molecules, then it will be harder for the water molecules to force the ions to dissociate. This can lead to ionic compounds that are insoluble in water, where very little of the compound will dissolve and dissociate into ions. Solubilities of ionic compounds have a large range of values as indicated in this list, where the values are given in grams dissolved per liter of water. Compounds with solubilities of hundreds of grams per liter of water are considered soluble and assumed to completely dissociate, so they would make for strong electrolytes. Whereas compounds with solubilities of 10 grams or less per liter of water are considered insoluble, and the amount of ions that dissociate in solution is so small as to be considered insignificant. So these would be considered non-electrolytes, or maybe in the case of lead chloride, a weak electrolyte. To determine the solubility of an ionic compound, simply refer to this chart of rules that is organized by ions. These solubility rules are provided on the back of the periodic table handout for quizzes and exams and do not need to be memorized, but you should practice using the table of rules as it can still be confusing. Note that the top portion represents all the ions that usually make a compound soluble. So if one of these ions is contained in an ionic compound, then you know that that compound will be soluble. Some exceptions to these types of compounds are listed on the right, and these would be for compounds that are insoluble. On the bottom portion, this represents ions that usually make a compound insoluble. So if you found one of these ions in a compound, you would assume that the compound is insoluble. But there are some exceptions to these rules as well. So the exceptions on the right this time are for those compounds that would be soluble. One of the biggest rules that most students miss is that any compound that contains a group 1A cation, so a cation from the first column of the periodic table, will be soluble. And it won't matter what anion you have. As long as you have one of these cations, you have a soluble ionic compound. The same goes for compounds with the ammonium cation or the nitrate anion. Compounds containing these ions are very common, and the more you start to recognize them, the easier it will be to identify them as soluble quickly. This concludes the third mini lecture for Chapter 8. Please note any questions you may have about this material and how it is utilized to solve problems in the suggested end of chapter exercises and the sapling homework for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our required class meetings, and during that time we will focus more on problem solving for concepts in this chapter.